We present the polar-photometric stereo for recovering surface normal by combining the polarimetric and photometric cues. Our method can be used under natural illumination. Classical photometric stereo can only recover the surface normal of Lambertian objects. It needs at least 3 images under different light conditions, and requires a dark room setting for experiment. In contrast, our method can be used for more general surfaces with different levels of specularity. By incorporating the polarimetric cue, we only need 2 light sources. Further, our method can be used in arbitrary uncontrolled environment. Photometric stereo estimates surface normals by observing the surface under different lighting conditions. Given known light directions L and observed intensity images I, the surface normal can be solved by inverting the linear equations formed by the Lambertian reflection model. Classical photometric stereo can only be applied to Lambertian surfaces, whose reflectance is perfectly diffuse. However, this assumption is unrealistic for many real-world surfaces, as specular reflections are very common. In our method, we use circularly polarized light to remove specularity. Under circularly polarized light, we can decompose the captured polarization image into linearly polarized, circularly polarized, and unpolarized components. As the specular reflection has the same polarization state as the light source, the circularly polarized component factors out the specular reflection, and leaving the unpolarized component as purely diffuse reflection, which is suitable for photometric stereo. The angle of linear polarization, or AOLP, is downgraded by the environment light, making it challenging to use polarimetric cue under natural environment. We solve this problem by illuminating the object with 2 circularly polarized light sources. Each enhances the AOLP on one side of the object. We then combine the 2 enhanced AOLP maps to obtain reliable polarimetric constraint for normal estimation. We combine 2 photometric constraints with the polarimetric constraint for an initial round of normal estimation. But the photometric constraints here are inaccurate as we have natural illumination in the scene. In order to mitigate the effect of natural illumination, we estimate a lighting proxy map to model the environment light. The lighting proxy map uniformly samples a hemisphere that is facing towards the object. For each surface point, we integrate the light intensity from all directions. We then compare the model with the observed image to solve the light intensity of each sampled point on the semisphere. We then iteratively refine the lighting proxy map and the surface normal estimations by fixing one set and solving for the other. We first evaluate our method with synthetic data. We use Mitsuba 2 to render polarimetric images of a target object with HDR environment map. We use the Areal captured PBRDF dataset to model the polarimetric surface reflectance. Here shows our normal estimation results of different surface materials and under various environment maps. We can see that our method is robust surfaces with different levels of specularity. We have built a prototype acquisition system and performed experiments under different indoor and outdoor environment. Our system consists of a monochrome polarization camera, and 2 circular polarized light sources. We use a quarter-wave plate retarder in front of the camera to measure circular polarization. The target object is placed around 50 cm away from the camera. Our method can greatly enhance the angle of polarization under environment light. Here we compare the angle of polarization directly measured under environment light and the fused results using our external light sources. We can see that our fused results are highly related to the object's surface geometry and are consistent under different environment light. We show our normal estimation result under indoor environment, and compare with other 2 state-of-the-art shape from polarization methods. As these methods cannot well handle the polarimetric cue affected by environment light, their results are highly inaccurate and suffers from various artifacts. Here is another comparison results in the outdoor environment where the environment light is stronger than indoor. Here are more results for both indoor and outdoor scenes. And we can recover surface mesh by integrating the estimated normal maps. Please visit our project website for more information about our work. Thank you for watching our video.